Welcome to the deep dive. We take some really fascinating source material, and we pull out the most important bits for you.
That's the idea.
And today, we're tackling a truly massive concept, one that's, well, fascinated humanity forever. Immortality.
Yeah, it's everywhere, isn't it? Ancient myths, cutting-edge science, deep philosophy. It really touches the core of, what it means to be human.
So our mission today is to help you navigate all that. We've got sources covering the science, the religion, the philosophy.
And we'll look at not just definitions, but the implications too. What would it actually mean to live forever? Expect some surprises, maybe a few aha moments.
Definitely. Okay, let's dive right in. Part 1, the scientific quest. Physical immortality.
Right. So scientifically, what are we talking about? Usually it means avoiding death, obviously, but also maintaining conscious thought.
And it's not just biological anymore, is it? The idea includes non-organic sources, like a computer.
Exactly. That's a more recent twist. Historically, the search was, let's say, a bit more mystical.
Like alchemy, the philosopher's stone.
Yeah, that sort of thing. Or you have legends like the Fountain of Youth, the Peaches of Immortality in Chinese myths, all looking for some kind of elixir. Early attempts, often quite magical or spiritual.
Fast forward to today, science looks at the causes of death differently. What are the big categories they think we could, theoretically, overcome?
Well, it mainly boils down to 3 things: aging, disease, and trauma.
Okay, let's unpack aging first. Aubrey de Grey has a specific take on this, doesn't he?
He does. He sees aging not as some mysterious force, but as basically accumulated damage. Changes at the molecular or the cellular level that mess up our metabolism over time.
Damage like what specifically?
He lists quite a few. Cells dying off and not being replaced, DNA damage, mutations in the nucleus, the oncogenic ones, problems with how genes are expressed, cells becoming senescent.
Senescent, those are the ones that stop dividing but hang around.
Exactly. Zombie cells, some people call them. Then there's mitochondrial mutations, junk building up inside and outside cells, things getting cross-linked, the immune system declining, endocrine changes.
Right.
It's a long list.
Wow. And his solution is?
He calls it engineered negligible senescence. Basically, a multi-pronged attack to repair all that damage as it occurs.
Sounds ambitious, like really ambitious. What does that actually involve? Fixing it?
Oh, it's not just one thing. It's a whole suite of potential therapies. Regenerating cells, fixing DNA, clearing out those senescent cells, boosting repair mechanisms, trying to keep the body's systems running like new, constantly maintained.
Okay, so aging is one hurdle. What about disease? That feels maybe more achievable.
Theoretically, yes. Technology could potentially overcome most diseases. Our understanding of genetics is exploding, leading to targeted treatments, cures even.
We're seeing that already, aren't we?
We are. Plus, better early detection, preventative medicine. Think about stem cells for Parkinson's or Alzheimer's, telomere research for cancer, new vaccines maybe for things like AIDS or TB.
Finding the genes linked to specific diseases.
Right, like type 1 diabetes, certain cancers, and even things like artificial nervous system devices restoring sight, for example. Drug development is always moving forward, too.
It's incredibly hopeful. But, okay, say we manage aging and disease. What about accidents? Trauma? The proverbial bus?
Ah, yes. Physical trauma, that's still a huge one.
Yeah.
Paramedic response, emergency medicine, they make a difference, but severe trauma is often fatal.
So what's the sci-fi solution there?
Well, the more speculative ideas involve things like nanotechnology, tiny robots inside you doing automatic self-repair almost instantly.
Wow.
But that raises other questions. If you're basically invulnerable, especially to brain trauma, how does that change your behavior? Would you become incredibly risk-averse? Would life even be desirable if you're constantly, bubble-wrapped?
That's a really interesting point. And then there's the environment itself.
Yeah.
You might be unkillable, but you still need resources.
Absolutely. You still need oxygen, food, water, overcoming aging, disease, trauma.
Yeah.
It doesn't make you immune to starvation or suffocation. Resource limits are real.
Which leads to this idea of actuarial escape velocity. Can you explain that?
Yeah, it's a fascinating concept. Think of it like this. Right now, every year you live, your remaining life expectancy generally goes down a bit.
Makes sense.
Actuarial escape velocity is the hypothetical point where medical science is advancing so fast that for every year you live, your remaining life expectancy actually increases by more than a year.
So you're literally outrunning death.
In theory, yes. Your expected lifespan keeps getting pushed further and further out, potentially indefinitely.
Okay, let's shift slightly. What about biological immortality that already exists? in nature.
Oh, it definitely exists. It means the absence of aging, the mortality rate, doesn't increase as the organism gets older chronologically.
And this relates to the Hayflick limit, cell division.
Yes. Most normal human cells can only divide a certain number of times the Hayflick limit. This is linked to telomeres.
The caps on our DNA, like shoelace tips.
Exactly like that. They protect the DNA, but they shorten with each division. Eventually, they get too short, and the cell stops dividing, becomes senescent, or dies.
But some cells overcome this.
Right. There's an enzyme called telomerase. It can rebuild those telomeres, allowing cells to keep dividing pretty much indefinitely. Our stem cells use it. And crucially,
Cancer
cells too, that's the double-edged sword. Uncontrolled cell division, thanks to telomerase, is a hallmark of cancer. It's a very tricky balance.
So finding that balance is key for human applications. Which organisms have crafted this naturally?
Well, bacteria, through binary fission, essentially create lineage immortality. Then you have Turritopsis dohrnii, this so-called immortal jellyfish.
The one that can age backward.
Sort of. Under stress, it can revert from its adult medusa stage back to a polyp, its juvenile form. It uses a process called transdifferentiation, basically resets its life cycle. It can do this potentially forever, which is why it's spread all over the world.
Incredible. Any others?
The freshwater polyp hydra is another classic example.
Yeah.
It shows negligible senescence, no signs of aging.
If they can do it, why do we age? It seems counterintuitive from an evolutionary standpoint. Why didn't we evolve not to?
That's a huge question in biology. There's no fundamental physical law like thermodynamics saying we have to break down. So why does aging exist? There are a few main theories.
Okay.
One is Peter Medawar's mutation accumulation idea. It suggests that mutations causing problems late in life, after you've likely reproduced, aren't strongly selected against by evolution. Nature doesn't really care what happens after you pass on your genes.
So bad stuff happens late because evolution's job is done by that.
Kind of, yeah. Then there's George C. Williams's antagonistic pleiotropy. This suggests some genes might be beneficial early in life, helping you survive and reproduce, but have negative effects later on, contributing to aging and death, a trade-off.
A double-edged sword again.
Right. And Thomas Kirkwood's disposable soma theory. This one focuses on energy allocation. Organisms have limited energy, and they have to split it between metabolism, reproduction, and maintenance or repair of the body, the soma.
Soma meaning the body cells, not the reproductive cells.
Yeah. Correct. The theory argues that evolution prioritizes reproduction over perfect long-term maintenance. So the body is disposable, built well enough to last through reproduction, but then gradual deterioration is accepted, essentially.
So mortality might actually be an evolutionary feature, not a bug. A necessary compromise.
That's how these theories frame it, yes. It's not necessarily an oversight, but perhaps a consequence of optimizing other things, like reproductive success or resource use across generations.
Which highlights the difference between the individual organism and the germline.
Exactly. Individuals die, but the germline, the reproductive cells, sperm and egg, connects generations and is potentially immortal. Zhores Medvedev pointed out that processes like recombination during meiosis and superior DNA repair in germ cells keep that lineage going, maintaining integrity in a way our somatic cells don't.
Okay, bringing it back to humans and technology.
Sure.
What are the main prospects for achieving biological immortality for us?
Well, one avenue is manipulating telomerase. Remember the mouse study? Mice engineered with much higher telomerase levels lived significantly longer, like 50% longer.
For the cancer risk.
Always the cancer risk. That's the major hurdle that needs solving before telomerase therapy becomes viable. It's a huge focus of research.
Yeah, on that.
Then you get into broader technological immortality. This is the idea that a combination of advances nanotechnology, better emergency medicine, genetics, bioengineering, regenerative medicine could dramatically extend lifespan.
This is the swallow the doctor idea, nanobots.
Precisely. People like Robert Freitas theorize about medical nanorobots patrolling our bodies, killing cancer cells, fighting bacteria, maybe even using gene therapy and nanotech to make the body self-sustaining, barring major trauma.
K. Eric Drexler, Rick Kurzweil.
Yeah.
They talk about this too.
Yes, Drexler envisions cell repair machines. Kurzweil famously predicted nanorobotics could reverse aging by around 2030, perhaps a bit optimistic, but it shows the direction of thought. It all echoes Richard Feynman's idea, prompted by Albert Hibbs, of swallowing the surgeon, the tiny machines doing the work internally.
Wild.
Yeah.
Okay, what about just pausing things? Cryonics.
Cryonics is exactly that. preserving bodies, or often just the brain, at ultra-low temperatures, stopping decay. The hope is future technology will allow revival and repair.
Does it work? I mean, the freezing part.
Modern techniques use vitrification. It's rapid cooling to a glass-like state, which avoids forming damaging ice crystals, especially important for the brain's delicate structures. Whether revival is possible, that's still entirely theoretical.
And if we can preserve the brain, what about copying it, mind uploading?
Yeah. Mind-to-computer uploading. The idea is to somehow scan and transfer your consciousness, memories, personality, everything into a computer, or maybe even a new body, organic or robotic.
Futurists like Moravec and Kurzweil are big on this.
They are. They envision potentially living indefinitely in a virtual world, or downloading into different forms.
But is the upload really you? Or just a copy? That feels like a massive philosophical problem.
It's the philosophical problem with uploading. How would you even do it? Gradually replace brain parts with hardware. Detailed scans. Would the original brain survive? And critically, is consciousness transferable or just copyable? If it's just a copy, the original you still dies. We just don't know enough about consciousness to answer that yet.
A huge question mark there. Lastly, in the tech realm, cybernetics.
Yeah.
Becoming cyborgs.
Right. Enhancing or replacing biological parts with technology. Brain implants, robotic limbs, artificial organs, maybe even a fully artificial body housing the brain. Theoretically, a sufficiently advanced cyborg could be immune to aging and disease. Maybe not trauma, but pretty close to immortal.
Okay, so the science is pushing boundaries, asking really fundamental questions. But for most of history, immortality wasn't about tech, was it? It was about the soul.
Exactly. Pre-21st century, it was almost entirely about the immaterial soul, the afterlife, which brings us into the realm of religion and philosophy.
Let's start with the Abrahamic traditions, Christianity.
Christian belief often starts with Adam and Eve losing physical immortality in the fall. But a core tenet found in the Nicene Creed is belief in a future resurrection, not just spiritual, but physical rebuilding at the second coming.
Paul the Apostle talks about transformed bodies.
He does. Bodies becoming like Christ's glorious body. Theologians like N.T. Wright use analogies like God downloading our software onto his hardware until new bodies are provided in a renewed creation, heaven and earth joined.
Are there figures in Christian tradition said to be physically immortal?
There are apocryphal stories like Cartaphilus, the wandering Jew, cursed to live until the second coming. And some early church fathers linked the immortal, rational soul to being made in the image of God.
Interesting. What about Islam?
Islam strongly emphasizes spiritual immortality. After death, there's judgment, leading to an eternal existence in either Jannah, paradise, or hell. The Quran famously says every soul will taste death, highlighting that physical life is temporary.
What about other beings? Angels, jinn.
Angels are generally seen as immortal, though there's some scholarly debate. Jinn are believed to have very long lives, maybe thousands of years. Certain figures like Khidr and Jesus are considered to have been granted exceptionally long lives by God, with Jesus prophesied to return. Even the Dajjal, the Antichrist figure, is said to have a long lifespan.
In Judaism, you mentioned their idea of the soul evolved.
Yes, the idea of a distinct immortal soul wasn't really prominent before the Babylonian exile. It developed later, influenced by Persian and Greek thought. The Hebrew word nephesh originally meant more like living being or life force, not an immortal entity separate from the body.
What about the afterlife, Sheol?
Sheol initially was just the grave, the state of being dead. Later ideas developed. By the Second Temple period, you had diverse views. Some texts, like 2 Maccabees, talk about physical resurrection. Others, like Enoch, describe it in detail. The Sadducees rejected any afterlife, while the Pharisees generally believed in resurrection, or perhaps just the soul's immortality, maybe even reincarnation for the good.
So where did Rabbinic Judaism land?
The mainstream rabbinic view became belief in the resurrection of the righteous dead in the Messianic age, leading to immortality. But it took time to solidify.
Okay, moving eastward to Indian religions. Hinduism.
Hinduism centers on the immortal soul, the Atman, trapped in samsara, the cycle of birth, death, and rebirth. Your karma determines your next life. The goal is moksha, liberation from this cycle, achieving eternal bliss or union with the ultimate reality.
Is physical immortality ever mentioned?
The Upanishads do hint at a state of physical immortality achievable through purification. And interpretations like Maharishi Mahesh Yogi's of the Bhagavad Gita suggest attaining eternal life by transcending duality. There's also the story of the Tamil Saint Valar, claimed to have achieved physical immortality and simply vanish.
And Buddhism seems almost counter to this, with non-self.
It does. The core Buddhist teachings of anatta, non-self, and anicca, impermanence, directly challenge the idea of a permanent, unchanging soul. Existence is seen as a flux of interconnected phenomena, the five skandhas or aggregates making up a person.
No room for an immortal soul there.
Generally, no, but there is a fascinating teaching in Tibetan Buddhism, Dzogchen, about achieving the rainbow body, where an advanced practitioner's physical body dissolves into light at death, leaving nothing behind, a kind of ultimate transformation, arguably a form of immortality.
Wow, okay, back to ancient roots. Ancient Greece. Their view seems complex too.
Yeah, early Greek belief often emphasized the unity of body and soul. A soul alone in Hades was a mere shadow, not truly alive, but certain heroes or favorites of the gods were believed to gain physical immortality. Ganymede, Menelaus, whisked away to eternal life.
And resurrection.
Some figures, like Achilles or Heracles, were sometimes thought to have been resurrected to immortality. But generally, the Greeks were skeptical, even hostile to resurrection. Look at Asclepius, zapped by Zeus for bringing people back from the dead. Philosophers like Plutarch later emphasized the soul separating from the body as true liberation.
And Zoroastrianism, its influence.
They believed the soul leaves the body a few days after death for judgment, heading to heaven or hell, ideas that clearly influenced Judaism, Christianity, and Islam. They even have a month named Amrdad, deathless, celebrating immortality's symbolic triumph.
What about philosophical traditions that aren't strictly religions, like Taoism?
Taoism presents an interesting case. Some texts, like the Luxi Chungui, state death is natural and unavoidable. Yet, some scholars, like Henri Maspero, saw Taoism historically as very focused on achieving physical immortality through alchemy and specific practices.
But others disagree.
Yes, scholars like Isabel Robinette argue it's more about living in harmony with the Tao, a way of life, not just a quest for endless physical existence. However, texts like the Tractate of Actions and the Retributions do talk about spiritual immortality, ascending to higher realms as a reward for good deeds. So there are different strands.
This all leads nicely into the purely philosophical arguments for the soul's immortality, separate from religious doctrine.
Absolutely. This is where logic and reason take center stage. Thinkers trying to prove the soul must endure.
Who are the key figures here? Plato seems central.
Plato is foundational, especially in his dialogue Phaedo. He laid out several arguments that philosophers wrestled with for centuries. Before him, Alcmaeon of Croton argued the soul's constant motion meant it couldn't stop.
What were Plato's main arguments?
He had four big ones. First, the cyclical argument. Things come from their opposites. Life from death, death from life. It implies a continuous cycle where the soul, bringing life, must persist.
Okay.
Second, the theory of recollection. We seem to know things at birth, like mathematical concepts, that we didn't learn empirically. Plato argued this means the soul must have existed before birth to learn them.
Innate knowledge implies a pre-existing soul. Got it.
Third, the affinity argument. The soul is invisible, non-composite, intellectual, like the eternal forms, whereas the body is visible, composite, physical. The soul has an affinity with the immortal realm, the body with the mortal. Therefore, the soul likely survives the body's dissolution. The argument from form of life. This is often seen as his strongest. The soul, by its very definition and function, participates in the essential form of life. Since it embodies life, it cannot admit its opposite, death. Therefore, the soul must be deathless, immortal.
That's quite a case. Did others build on these?
Definitely. Platonists argued the soul's simplicity means it can't decompose. Metochites focused on its self-moving nature. Avicenna used thought experiments to argue for its distinctness from the body.
What about later, maybe more familiar names?
Aquinas integrated Aristotelian ideas with Christian theology. Descartes argued from the soul's simplicity, lack of parts, that it couldn't decompose, though he admitted God could just annihilate it. Leibniz also used the simplicity argument and later developed his idea of immortal monads.
And Moses Mendelssohn.
Yes, in his Phaedon, he revisited and defended Plato's arguments, particularly simplicity, trying to shore them up against criticisms. He added arguments like simple things can't just vanish into nothing, and the soul retains potential even when dormant, like in a coma.
Okay, we've covered a lot: science, religion, philosophy. Let's pivot to the ethics and societal impact. If immortality became possible, what happens then?
That's where it gets incredibly messy and challenging. The ethical questions are huge. Think about persistent vegetative states, kept going forever. What about personality changes over centuries? Is it still you?
The mind-copying issues we touched on.
Exactly. And the immediate stark issue. Who gets it? Would it create massive social and economic divides? Immortality for the rich.
And there's the flip side. Maybe immortality isn't even desirable. Maybe it's a curse.
That's a powerful counter-narrative. The myth of Tithonus eternal life, but not youth, just endless decay. Mary Shelley's The Mortal Immortal, watching everyone you love die, it's portrayed as torment.
Shelley Kagan's dilemma captures this, right?
Perfectly. Kagan argues you face a dilemma. Either your character stays the same, and eventually over infinite time you'll get crushingly bored, or your character changes radically, memories wiped, personality altered, but then is that future being really you anymore? Would you care about its existence?
So his conclusion is
that maybe the best we can hope for is to live a good long life as long as we find it valuable, and then accept death gratefully when the time comes. Makes you think, doesn't it?
it really does. What about the broader society? How would losing mortality change social structures?
Fundamentally, so much of our behavior, our urgency, our institutions are shaped by the fact that life is finite. Take that away and, well, who knows? We're already seeing shifts with aging populations globally that might be a small preview.
The sociology of immortality.
Yeah, it's a growing field. Looking at how we already try to extend life or memory online memorials, the push for biomedical longevity. Some imagine a post-mortal society, maybe hyper-technological, maybe something else entirely.
And the environmental impact.
Huge. Immortality implies potentially massive population growth, straining resources, the planet itself. That's a major, major challenge.
Politically, is this getting any traction? Are governments funding immortality research?
Not really on a large scale, not explicitly aiming to stop aging. There aren't big international programs. But you do have pro-immortality political parties popping up.
Really? Where?
Places like Russia, the US, Israel, the Netherlands. Small parties, usually, but their goal is specific. Push for government support for anti-aging research and make any resulting technologies widely accessible.
But the critiques are strong too, aren't they? Creating an immortal elite.
Very strong. Many scholars worry it would just exacerbate inequality, heighten stratification, a permanent upper class. Others see it as the ultimate capitalist project, extending life mainly for the wealthy elite who can afford it. It could become a real political battleground.
Before we finish, let's quickly touch on the symbols. Humanity has used symbols for immortality forever, it seems.
Absolutely. They're everywhere. The Egyptian ankh, symbol of life. The Mobius strip, endless loop. The Ouroboros, the snake eating its tail cycle, renewal.
Tiny symbols too?
Yes. The fungus of longevity, the peaches of immortality, the character 10 for eternity, the phoenix, rebirth from ashes, even the peacock in Christian symbolism, because its flesh was thought not to decay. Colors too, amaranth, peach, all signifying endless life.
So we've really taken a journey today through the scientific quest, the diverse religious views, the philosophical arguments, and these really complex ethical and societal questions.
We aim to pull out the key insights from all these different angles, hopefully giving you a solid, well-rounded perspective on this ancient dream and increasingly this modern ambition.
What stands out is just how persistent this desire is, this quest to transcend our limits, whether through ancient magic, spiritual belief, or cutting-edge tech.
It really is fundamental. From elixirs to nanobots, it's the same underlying drive.
Which leaves us, and you, with a final thought to chew on. Given everything we've explored, the potential, the promise, but also the profound downsides and ethical dilemmas, what do you think is the biggest challenge or maybe the greatest gift hidden within this idea of living forever? Ever wondered what really happens after you take that first bite? I mean, it's more than just food disappearing, isn't it?
Oh, absolutely. It's this incredibly complex, fascinating, and sometimes pretty surprising internal journey your body takes, every single time you eat.
So today, we're doing a deep dive into one of your most fundamental systems, the human digestive system.
Yep.
We've pulled together some really detailed sources that lay out the whole process, basically from mouth to, well, the final exit.
Our mission today really is to unpack this intricate system. We want to highlight its incredible efficiency, who the key players are, and even some historical bits that show just how long we've been trying to figure this all out.
Yeah.
By the end, you'll have, I think, a whole new appreciation for what your body's doing, like silently all the time.
Okay, let's dive in then. What's really kind of amazing is that digestion actually kicks off before any food even hits your tongue. It's this thing called the cephalic phase.
That's exactly right. Just, seeing food, smelling it, even just thinking about your favorite pizza
Yep.
can trigger your brain. It sends signals, gets your gastric glands ready, prepares for action. Then, okay, food enters the mouth and the real action starts, both mechanical, chewing, and chemical breakdown.
Right.
Your mouth has these salivary glands, several pairs, plus lots of tiny ones constantly making saliva. And saliva seems simple, but it's actually this really complex mix.
So it's not just wet stuff.
Not at all. It moistens food, softens it up, makes it easier to swallow. It even protects your teeth with mucus, specifically a protein called mucin.
Okay, so saliva's doing a lot more work than I thought.
Definitely. And here's where it gets really interesting, I think. Saliva has key digestive enzymes.
Like what?
Well, amylase, for one, it jumps right in, starts breaking down starches into simpler sugars, maltose, dextrose.
Right away.
Instantly. And then there's lingual lipase. It begins breaking down fats. This is super important for babies, actually, because their main fat enzyme system isn't fully online yet.
Oh.
And beyond just digestion, saliva has antibodies, so it plays an immune role. Plus, it's got this unique protein, haptocorin, that acts like a little bodyguard for vitamin B12.
The bodyguard.
Yeah, it grabs onto B12 and shields it through the really harsh, acidic stomach environment. Pretty clever.
Incredible. And the tongue, I mean, it seems like just a muscle, but it's obviously doing a lot here too.
Oh, massively.
Yeah.
Your tongue is this fleshy, muscular sensory organ. It's where you first get that sensory input from food via your taste buds.
Right, the taste buds.
If the taste is good, the tongue just springs into action, moves the food around, mixes it with more saliva. It's got two sets of muscles, which gives it amazing mobility for chewing and getting that food ready to swallow.
So why do we have these specific tastes, like the 5 basic ones?
Right, good question. Taste itself is chemoreception, right? It happens in these specialized receptors, mostly on the tongue, but also surprisingly a bit on the epiglottis and even the upper esophagus. So the 5 basic tastes: saltiness, sourness, bitterness, sweetness, and umami. Think of them as signals from evolution. Signals.
Yeah. Saltiness and sourness help you manage salt and acid balance. Bitterness. Well, that's often a warning sign for poisons. Lots of plant defenses are bitter,
Okay, that makes sense.
Sweetness signals energy carbs, basically, especially once that salivary amylase starts working. And umami points towards protein-rich foods.
So your brain's making super quick decisions.
Instantly. Is this safe? Is it nutritious?
Yeah.
And taste works so closely with smell, doesn't it, to create those complex flavors we enjoy.
Right. And then the teeth, can't forget those, the grinders.
Exactly. Your teeth made of dentin, covered in super hard enamel, the hardest stuff in your body.
Harder than bone.
Yep. And they're specialized. Incisors cut, canines tear, and the premolars and molars, they do the heavy-duty chewing and grinding.
And all that chewing is important because
It massively increases the surface area of the food, makes it much easier for those digestive enzymes we talked about to get in there and do their job.
So all this chewing, mixing with saliva and mucus, it forms this soft, wet ball of food called a bolus, ready for the next step.
So bolus formed, ready to swallow. There's like
Yeah.
a traffic controller at the junction, right? The epiglottis.
That's a great way to put it. The epiglottis, it's this neat little flap of elastic cartilage right at the entrance to your larynx, your voice box. It even has some taste buds.
Really?
Yeah. But its critical job, its life-saving function, is folding down when you swallow. It acts like a lid, sealing off your windpipe, the trachea.
So food doesn't go down the wrong way.
Exactly. It directs the food safely towards the esophagus. And if, by chance, something does slip into the larynx, your body has this powerful cough reflex. It's like a built-in eject button to protect your lungs. Amazing system.
Okay, so from the mouth, the bolus moves into the pharynx.
Right, the pharynx. It's a shared space. Air goes through it. Food goes through it.
How does that work?
Well, when you swallow, the body prioritizes the food. It momentarily blocks the airway. Then muscles in the pharynx kind of push the food along into the esophagus.
And the esophagus, that's the food pipe, basically.
Precisely. It's a muscular tube, maybe 25 centimeters long, give or take. Connects the pharynx down to the stomach.
Is it just a smooth tube?
It's muscular, and it has sphincters, like muscular gates at both ends. The upper one opens to let the bolus in when you swallow.
And the lower one?
The lower esophageal sphincter, yeah. That one's super important. It guards the entrance to the stomach and normally stays tightly shut.
Why is that so crucial?
To keep all that strong stomach acid and digesting food in the stomach, preventing it from splashing back up into the esophagus.
Heartburn.
Exactly. When that sphincter doesn't work quite right or it relaxes when it shouldn't, you get reflux. That's the burn.
Okay, So how does the food actually get down the esophagus? Does it just drop?
You'd think so, but
Mm.
no, not just gravity. It's moved along by this rhythmic, wave-like muscle contraction. It's called peristalsis.
Peristalsis.
Yeah, these waves squeeze the bolus downwards, and this peristalsis, this muscular wave action, it doesn't stop at the esophagus. It continues all the way through your digestive tract.
Really, all the way.
Yep, it keeps everything moving along. In the stomach, this motion helps mix everything up and starts forming this semi-liquid stuff called chyme.
Chyme. Got it.
And actually, speaking of things nearby, the diaphragm, the big muscle under your lungs that helps you breathe,
Yeah.
it plays a small but interesting role in digestion, too. It helps anchor your liver in place, and there's even a little muscle attached to it that helps widen a bend in your small intestine, easing the passage of food.
Huh. Who knew? Okay, so the bolus, pushed by a peristalsis, gets past that lower sphincter and arrives in the stomach, the command center, right?
You could definitely call it that. And it's way more than just a storage bag. It's a real chemical processing plant.
It looks kind of J-shaped in diagrams.
Typically, yeah. And it's incredibly stretchy. An adult stomach can comfortably hold about a liter of food and liquid. A newborn's. Only about 30 milliliters. And inside, that peristalsis churning continues, mixing the food vigorously with really potent digestive juices.
Gastric juice. What's in that?
Primarily, it's hydrochloric acid, really strong acid, and some sodium chloride. There's a hormone called gastrin that tells the stomach to produce this juice.
And the acid does what?
It does a few things. It kills a lot of bacteria, and importantly, it activates digestive enzymes. The main protein-digesting enzyme is pepsin.
Pepsin.
Yeah, but here's the clever bit. The stomach doesn't secrete active pepsin. It secretes an inactive form called pepsinogen.
Like a safety lock.
Exactly. So it doesn't start digesting the stomach wall itself. Only when pepsinogen hits the strong acid does it activate and become pepsin, ready to chop up proteins.
Smart. Any other enzymes?
There's also gastric lipase, which starts working on fats, but honestly, it's not as powerful as the fat enzymes that come into play later on.
So with all this acid and protein chopping enzyme, how does the stomach not just digest itself?
Excellent question. Protection is key. The stomach lining is coated in this thick, slimy layer of mucus. Millions of tiny glands are constantly producing it. It forms a physical barrier against the acid and the pepsin.
Okay, that makes sense. But earlier you mentioned vitamin B12 needed protection through the stomach acid. How does that survive?
Ah, yes, the B12 journey. It's a fantastic example of teamwork. It's a two-step process. Remember that haptocorin protein from saliva?
The bodyguard, yeah.
Right. It binds to B12 in the mouth or throat and protects it all the way through the stomach's acid bath. Then, when the chyme moves into the less acidic small intestine, stomach enzymes break down the haptocorin.
Freeing up the B12.
Exactly. And just at that moment, another protein called intrinsic factor, which is made by specific cells in the stomach lining.
Okay.
Intrinsic factor steps in, binds to the now free B12, and carries it further down the small intestine to where it can finally be absorbed. It's like a carefully planned handoff.
Wow. Quite the relay race. So what leaves the stomach then?
What leaves is this thick, semi-liquid mixture called chyme. Making it can take, I don't know, an hour or two, maybe longer, depending on the meal.
Okay.
This time then passes, bit by bit, through another muscular gate, the pyloric sphincter, into the very first part of the small intestine, the duodenum.
Right, the duodenum. And once that chyme gets there, it's not working alone, is it? This is where those accessory organs really jump in.
Absolutely. This is where the orchestra really comes together. You've got the pancreas, the liver, the gallbladder, all working in perfect sync with the small intestine.
Let's talk pancreas first. I know it does insulin stuff, blood sugar.
Right, that's its endocrine role. But for digestion, it's a powerhouse exocrine gland. It produces pancreatic juice.
Okay, and what's special about that?
Two main things. First, it's alkaline. It contains lots of bicarbonate ions. These are crucial for neutralizing that superacidic chyme coming from the stomach. The intestine needs a more neutral environment for its enzymes to work.
Ah, okay. Neutralizing the acid. And the second thing,
Enzymes, a whole cocktail of them. It makes powerful enzymes to break down proteins, fats, and carbohydrates. Think trypsin and chymotrypsin for proteins, lipase for fats, amylase for carbs.
the full toolkit.
Pretty much. And again, just like pepsin in the stomach, many of these are released in inactive form zymogens, so the pancreas doesn't digest itself. They only switch on once they safely reach the intestine.
It's a very clever system.
Yeah.
Okay, what about the liver? Huge organ, does tons of things.
Yeah.
What's its main digestive job?
You're right. The liver's a multitasker: detox, protein building, glucose storage. But for digestion, its primary role is making bile acids and lecithin. These are essential for breaking down fats, and it produces the bile fluid itself.
Bile.
Bile is mostly water, but it contains those bile salts, mucus, pigments like bilirubin, which comes from breaking down old red blood cells, gives waste its color,
Yeah.
and fats. This bile gets sent to the gallbladder.
Right. The gallbladder doesn't make bile, it just stores it.
Exactly. It's a little storage sac tucked under the liver. It holds the bile produced by the liver, and importantly, it concentrates it, makes it more potent.
So how does it know when to release the bile? It can't just be leaking out all the time?
No, it's very precise. It's triggered by a hormone called cholecystokinin, CCK.
CCK.
Yeah. As soon as fatty chyme enters the duodenum from the stomach, it triggers cells there to release CCK into the bloodstream. CCK travels to the gallbladder and signals it to contract.
Go squeeze out the bile.
Right into the duodenum, just where it's needed to tackle those fats.
And what does the bile actually do to the fats?
Its key role is acting as an emulsifier, like dish soap breaking up grease. Bile salts surround large fat globules and break them into much, much smaller droplets called micelles.
Micelles, okay.
This massively increases the surface area of the fat, so the fat-digesting enzymes, the lipases mainly from the pancreas, can attack them much more effectively. Bile also helps you absorb fat-soluble vitamins like vitamin K.
So without bile, fat digestion would be really difficult.
Extremely inefficient, yes. And if things go wrong with the bile, maybe too much cholesterol or the gallbladder doesn't empty properly, those components can crystallize and form gallstones.
Ouch. Okay, so we've got neutralized chyme, pancreatic enzymes, and bile all meeting in the duodenum. Now we're properly in the small intestine, the main event for digestion and absorption, right?
Absolutely. This is where the vast majority of digestion and nutrient absorption happens.
You mentioned neutralization is key.
Crucial. That bicarbonate from the pancreas, plus some bicarbonate-rich mucus from glands in the duodenum itself, and the alkaline bile, they all work to bring the pH up, protecting the intestine and letting all the enzymes do their best work.
And the main job now is breaking stuff down small enough to absorb.
Exactly. Breaking down carbohydrates into simple sugars, proteins into amino acids, fats into fatty acids and glycerol. Small molecules that can pass through the intestinal wall into your body.
And how does the small intestine actually absorb all this stuff? It must have a huge capacity.
It does, thanks to its incredible structure. The lining isn't smooth. It's covered in these specialized cells called enterocytes, and the lining is folded, and on those folds are millions of tiny finger-like projections called villi.
The villi? I heard of those.
And then each cell on the surface of the villi has even tinier projections called microvilli. All these folds, villi and microvilli, create this absolutely enormous surface area.
Like how enormous?
Some estimates say if you flattened it all out, it could cover a tennis court.
No way. Inside your belly.
It's incredible. This huge surface area is vital for efficiently absorbing all those digested nutrients. Some final digestion even happens right on the surface of the microvilli by enzymes located there.
Okay, tennis court surface area.
Yeah.
Wow. What about those fats, the micelles? How do they get absorbed? It's different, right?
It is slightly different. Once fats are broken down, they get repackaged inside the intestinal cells into these little particles called chylomicrons. Think of them as tiny fat delivery trucks.
Okay.
Now, unlike most other nutrients that go directly into the bloodstream capillaries in the villi,
Yeah.
these chylomicrons, these fat trucks, are too big for that. They get absorbed into tiny lymph capillaries called lacteals, which are also present in the villi.
Lacteals. So they go into the lymph system first.
Exactly. This mixture of lymph and chylomicrons creates a milky-looking fluid called chyle. This chyle travels through the lymphatic system and eventually gets dumped into your bloodstream near your heart. So fats take a slightly different route.
Fascinating. And the small intestine isn't just one long tube, is it? It has sections.
Right. 3 main sections. First is the duodenum, the short C-shaped part right after the stomach. That's the main mixing bowl, receiving chyme, bile, pancreatic juice.
Okay.
Then comes the jejunum, the middle section. It has lots of prominent circular folds to maximize that surface area. This is where most of the absorption of sugars, amino acids, and fatty acids happens.
Jejunum. Got it.
And finally, the ileum. That's the last and longest part. Its main jobs are to absorb vitamin B12, remember, bound to intrinsic factor, and also to absorb bile acids so they can be recycled back to the liver and mop up any remaining nutrients that escaped absorption earlier.
Okay. So from the ileum, what's left moves on. Where does it go next?
It moves into the final stages. First, it passes through the ileocecal valve, another one-way gate into the cecum.
The cecum.
Yeah, it's this pouch that kind of marks the beginning of the large intestine. That ileocecal valve is important. It slows down the passage from the ileum, giving a bit more time for absorption. And fun fact, the appendix is attached to the cecum.
Ah, the appendix. Okay, so after the cecum, we're into the large intestine proper.
Correct. The large intestine, which includes the colon, the rectum, and finally the anus.
And things move much slower here. Right?
Much, much slower. Transit time through the large intestine can be anywhere from, say, 30 to 40 hours, sometimes longer.
Wow. Why so slow? What's its main job?
Its main functions are really about reabsorbing water from the remaining indigestible food matter. It also absorbs some electrolytes, some minerals, and critically, it's home to trillions of gut bacteria, the gut flora or microbiome.
The microbiome. We hear a lot about that.
Yeah, and these bacteria do important work. They ferment some of the indigestible material, like certain fibers, producing vitamins like some B vitamins and vitamin K and short-chain fatty acids that can actually nourish the colon cells.
So it's mostly about water absorption and bacterial action.
Largely, yes. What's left after the water's removed and the bacteria have done their thing is the semi-solid waste we call feces.
And how does that get moved along and eventually out? Still peristalsis.
Yep, coordinated peristalsis is still the driver. The large intestine has specialized muscle layers. There's an outer layer of longitudinal muscles that are gathered into 3 bands called the taenia coli.
Taenia coli.
Yeah, these bands are slightly shorter than the colon itself, which causes the colon wall to bulge outwards between them, creating those characteristic sacs or pouches called haustra.
Ah, those bulges you see in diagrams.
Exactly. And then there's an inner layer of circular muscle. These muscle layers work together to slowly propel the feces along, segment by segment, towards the rectum, ready for elimination.
Incredible. Yeah. Beyond the main organs, though, you mentioned support systems. How does this whole massive operation get its blood supply? It must need a lot of energy.
It definitely does, especially after a meal. The digestive system has a really rich blood supply from major arteries branching off the aorta.
Like which ones?
Well, there's the celiac artery supplying the upper part stomach, liver, spleen, pancreas. Then the superior mesenteric artery takes care of most of the small intestine and the first part of the large intestine.
Okay.
And the inferior mesenteric artery supplies the rest of the large intestine down to the rectum.
And the blood flow changes.
Oh yeah, dynamically. Blood flow to the gut can increase significantly, peaking maybe 20 to 40 minutes after you eat, and it can stay elevated for a couple of hours while digestion and absorption are in full swing. It's diverting resources to where they're needed.
Makes sense. And maybe the most fascinating support system, the second brain, the enteric nervous system.
Ah, yes, the ENS. It truly is like a second brain. We're talking about something like 100 million neurons. That's more than in your spinal cord.
100 million. Where are they?
They're embedded right there in the walls of your entire GI tract, from the esophagus all the way down to the anus. They're organized into these intricate networks or plexuses.
So the gut can think for itself, kinda.
To a large extent, yes. It can control gut motility, secretion, blood flow, largely independently of the actual brain. That's why it gets called the second brain.
But the main brain still has some input.
Oh, definitely. It's influenced by the autonomic nervous system. The parasympathetic system, mainly via the vagus nerve, generally stimulates digestion, the rest, and digest functions.
Okay.
And the sympathetic system, the fight or flight response, tends to slow digestion down, diverting resources elsewhere during stress. It's this complex interplay, constant communication.
It's just staggering how complex this all is.
Yeah.
Thinking about how it develops. It must be incredible to watch unfold in an embryo.
It truly is. The very early gut tube actually forms from parts of the yolk sac. And then around the 4th week of pregnancy, some really key movements happen. The stomach rotates, settling into its position on the left side.
It rotates.
Yep. And at the same time, little buds start to grow out from the duodenum. These will eventually develop into the liver, the gallbladder, and the bile ducts. It's a precisely choreographed sequence, biological engineering at its finest.
It sounds so robust, but obviously things can go wrong.
Okay.
We touched on heartburn and gallstones.
Yeah.
What are some other common issues, maybe further down the line?
Yeah, despite its resilience, every part is vulnerable. You can get infections, bacterial, viral, fungal, think gingivitis or thrush in the mouth. Medications can cause side effects too.
Right.
In the esophagus, besides reflux, you might have things like Schatzki rings, which are these narrowings that make swallowing difficult. The stomach can have issues like gastroparesis, where it empties too slowly, or gastritis, which is inflammation, or those peptic ulcers, often linked to the H. pylori bacteria.
Okay. And in the intestines?
Malabsorption is a big category. This means you're not absorbing nutrients properly. It could be due to infections or missing certain enzymes, or conditions like celiac disease. That's an autoimmune reaction to gluten damaging the small intestine lining.
Celiac disease, right.
Then in the large intestine, you have things like diverticulitis, where those pouches, the haustra, get inflamed or infected, and inflammatory bowel diseases like Crohn's disease,
Crohn's.
which can affect anywhere from mouth to anus, and ulcerative colitis, which mainly affects the colon and rectum. Both of those, unfortunately, increase the risk of developing colorectal cancer later on.
That's serious.
It is. And then there's irritable bowel syndrome, IBS, super common, causes cramping, bloating, changes in bowel habits. It's a functional disorder, meaning the gut looks normal but doesn't work right. Plus, things like parasitic infections like giardiasis. Lots can potentially go wrong.
How do doctors even figure out what's happening in there?
Various ways. Imaging is key. Sometimes they use things like a barium sulfate series. You drink this chalky liquid and it shows up on x-rays, outlining the shape and movement of your GI tract. Endoscopies, colonoscopies, lots of tools.
And cancer.
Yeah.
You mentioned the risk with IBD. How big a problem is digestive system cancer overall?
It's a major health issue, unfortunately. The stats are sobering. For 2023 in the U.S., estimates were around 348,000 new cases of digestive system cancers and about 172,000 deaths.
Wow. Which types are the biggest killers?
The leading causes of death in that category are colorectal cancer, then pancreatic cancer, which is notoriously difficult, followed by liver cancer, esophageal cancer, and stomach cancer.
That's significant.
It really is. And it's interesting, even things like bile acids, which are essential for digestion, if they reach abnormally high levels, they've been implicated as potential carcinogens in the gut. It's all about balance.
Even pregnancy can affect digestion, right? Like gestational diabetes?
Yes, that's considered a potential digestive disorder during pregnancy. It affects how your body processes sugar and can sometimes lead to other complications as well. The hormonal shifts during pregnancy can impact the digestive system in various ways.
Okay, so we've covered how it works, development, problems. How did we even figure all this out? What's the history of understanding digestion? Must have been a mystery for ages.
Oh, for centuries. Our understanding has definitely evolved. If you go way back to the 11th century, someone like Avicenna, a great Persian physician, he believed digestive problems caused gas pretty accurate and suggested lifestyle changes.
Ahead of his time.
In some ways. But for a long time, the stomach was seen quite negatively. It wasn't until the mid-17th century that Jan Baptist van Helmont gave the first chemical explanation of digestion. That was a big shift.
And the acid discovery.
That was William Prout in 1823. Discovering hydrochloric acid in gastric juice was huge. It started to explain the chemical power of the stomach.
And then there's that amazing story about William Beaumont, the army surgeon.
Ah, yes. 1825. He had a patient with a gunshot wound to the stomach that never fully closed, creating a sort of window. Beaumont literally watched digestion happening live.
Incredible.
He described the churning motion, tested how different foods digested, earned him the nickname Father of Gastric Physiology. His direct observations were revolutionary.
So observation, then chemistry.
Yeah.
What came next?
Well, Pavlov, famous for his dog salivating.
Right.
In 1895, he showed that stomach acid secretion was linked to the nervous system, specifically the vagus nerve, a brain-gut connection.
Okay.
Then the 20th century brought a focus on hormones and enzymes. Discoveries like secretin and gastrin showed this complex chemical signaling controlling everything. Later came the drugs H2 blockers in the 70s, proton pump inhibitors in the 80s that could actually control stomach acid production, game changers for ulcers and reflux.
And the ulcer bacteria.
That was Marshall and Warren in 1983. Linking Helicobacter pylori to ulcers was Nobel Prize-winning work. It completely changed how we treated stomach ulcers, from stress management and bland diets to antibiotics.
Wow. What a journey of discovery. Any other surprising historical bits?
Well, here's a fun one related to ancient habits. Art historians noticed that in depictions of ancient Roman banquets, the diners are often reclining on their left sides.
On their left. Why?
The theory is it actually aids digestion. Lying on your left side uses gravity and the natural curve of the stomach to help food settle and process more comfortably. It gives the stomach more room to expand downwards.
Huh. So those Romans knew a thing or two, maybe without even knowing the science.
Seems like it. Practical anatomy, perhaps.
We have really journeyed deep into this incredible inner world today, haven't we? The human digestive system. From just thinking about food right down to the very end, it's just a testament to the body's efficiency and complexity.
It really is. It's this beautifully coordinated dance, isn't it? Every part playing its role, transforming food into energy and building blocks while also protecting us. It's an amazing internal symphony, constantly working away.
So what stands out most to you listening in about this incredible system? Maybe next time you sit down for a meal, you'll have a whole new appreciation for that silent, intricate process happening inside. And hey, maybe you'll even think about which side to recline on afterwards.
You know, there's a subtle but really powerful shift we feel as the year turns, isn't there? That feeling when the light seems to just, well, linger forever or vanish almost completely.
Yeah, that distinct sense of a turning point.
Exactly. It's more than just a date on the calendar. It feels like a cosmic pivot, a moment that's really resonated with people for, gosh, millennia.
Absolutely.
So today we're doing a deep dive into the heart of that phenomenon. The solstice.
Right.
We're going to peel back the layers, get beyond just knowing the dates. We want to understand the astronomy behind it, the mechanics, uncover the word's origin, which is fascinating in itself, and explore the really rich cultural stuff woven around these unique moments.
That's the plan. Our mission really is to break down how the Earth, the Sun, and all those celestial movements actually work together to create the solstices. And we'll dig into some, I think, pretty surprising facts and maybe some ancient wisdom too, because understanding the why behind it all makes the what those specific days feel much more meaningful for you.
So let's start right there. What is a solstice, fundamentally? At its core, it's an astronomical event. It happens when the sun hits its highest or lowest point in the sky relative to the celestial equator.
Its most northerly or southerly point, yeah. Like the peak or the trough of its apparent path.
Peak or trough, good way to put it. And it happens twice a year, usually around June 20th to 22nd, and then again December 20th to 22nd, give or take.
The June and December solstices.
And the word itself, solstice, is really cool. If you dig into it, the origin tells the story perfectly.
It does, yeah.
It's from Latin, sol, which means sun, and sister, meaning to stand still.
Sun standing still.
You can almost picture it, can't you? The sun's path seems to just pause at its northern or southern limit before it starts heading back the other way.
And that standing still idea is key, especially from our perspective here on Earth. Now, the sun's always moving west across the sky because, the Earth's spinning.
Sure, that doesn't stop.
But its vertical movement, its declination, that appears to stop for a moment, a literal sun standing.
Ah, okay.
And English actually used to have its own words for this sunstead, from the Old English sunsteed and also sunstay.
Oh, interesting. Sunstead.
Yeah, but they pretty much fell out of use after the 1600s or so.
Yeah.
Became quite rare.
Huh. So we know what it is the sun's standing still vertically and where the word comes from. But the big question is why? Why does this happen? What's really driving this whole cycle? The solstices and, well, the seasons themselves.
I mean, the fundamental cause. It really all boils down to one thing. Earth's tilt.
The famous tilt.
The famous tilt. Our planet's axis, the line it spins around, isn't perfectly upright compared to its orbit around the sun. It's tilted.
By about 23.4 degrees, right?
Exactly. Roughly 23.44 degrees.
Okay.
And the fancy term is the obliquity of the ecliptic, but basically it's just Earth's lean.
Yeah.
And crucially, that lean stays pretty much constant as we go around the sun. So it's not about being closer or farther from the sun.
Which is a common misconception.
A very common one. It's all about that tilt. That 23.44 degree lean changes the angle sunlight hits different parts of Earth throughout the year.
Like tilting a flashlight beam.
Precisely. That tilt is the engine behind the whole rhythm of the year.
That's a great way to think about it. And this constant tilt, it causes some really dramatic effects depending on where you are on the planet.
Oh, absolutely. For about half the year, one hemisphere, say the northern hemisphere, is tilted towards the sun. It gets more direct sunlight, longer days. That's summer.
Right.
Then for the other half, it tilts away, and the southern hemisphere gets its turn for more direct sun.
Okay. And you mentioned the subsolar point.
Yes. That's the exact spot on Earth where the sun is directly overhead, 90 degrees up. At the June solstice, that point reaches its northernmost latitude, 23.44 degrees north. That line is the Tropic of Cancer. And then, 6 months later, at the December solstice, the subsolar point is at its southernmost latitude, 23.44 degrees south, the Tropic of Capricorn.
And near the poles, this tilt leads to those incredible phenomena like the midnight sun.
Exactly. Within the Arctic Circle, during their summer solstice, the sun literally doesn't set for 24 hours or more. It just circles around the sky. Polar day.
Imagine trying to sleep.
Right. And conversely, at the opposite pole, you get the polar night. The sun doesn't rise at all. Deep winter darkness.
Wow.
And here's a little nuance that often surprises people. Even though the solstices mark the peak of sunlight intensity, the actual hottest or coldest days of the year usually lag behind by about a month or so, especially in temperate places.
Oh, right. Why is that?
It's because of Earth's thermal inertia. Think of it like, well, the oceans and the land take time to heat up after getting the most sun, and time to cool down after getting the least.
Like a giant pot of water on the stove takes a while to boil and a while to cool off even after you turn off the heat.
Exactly like that. Earth's like a big slow-cooking oven in that sense.
Okay, so solstices are the extremes, the longest and shortest daylight points, generally speaking. But they're part of a bigger cycle with the equinoxes. How do they relate?
Good point. So in a typical year, what we call a tropical year, you have 2 solstices and 2 equinoxes. They mark the turning points of the seasons.
Right.
While solstices are about the sun reaching its northernmost or southernmost points, equinoxes happen when the sun's path crosses directly over the Earth's equator.
And equinox means equal night, right?
Pretty much. Around the equinoxes, day and night are approximately equal in length everywhere on Earth, or at least at corresponding latitudes. That's the main difference. Solstices are extremes of light-dark. Equinoxes are points of balance.
Okay, balance versus extremes. But you mentioned something fascinating earlier about the equator, that the longest and shortest days don't always line up with the solstices there.
Ah, yes, that's a really neat exception. Our intuition, especially away from the tropics, is that the June solstice is the longest day, December the shortest, full stop.
Yeah, that's what I always thought.
But if you're very close to the equator, it gets weird. The day with the most daylight hours actually happens around, believe it or not, December 23rd.
Wait, after the December solstice?
Yep, and the shortest day isn't the June solstice either. It's around September 16th, near the autumnal equinox.
That's completely counterintuitive. Why?
It's complex, tied into the exact shape of Earth's orbit and how solar declination changes speed. But it's a fantastic reminder that our perspective really depends on our latitude. What seems obvious here isn't universal.
Wow. Okay, so measuring the effects like day length can be tricky. What about pinpointing the exact moment of the solstice itself? If the sun is standing still vertically, how hard is it to tell precisely when that happens?
That is a great question, and historically, it was really difficult.
Because the movement slows right down.
Exactly. The sun's change in declination, its north-south movement, becomes incredibly small as it approaches the solstice point. It's like trying to pinpoint the very top of a ball's arc when you throw it up. It hangs there for a tiny moment.
So old tools couldn't really catch that, like a gnomon, the stick in a sundial.
Right. Tools like gnomons or even more sophisticated astrolabes struggle to detect such tiny changes day to day around the solstice.
So how did ancient astronomers manage?
They used clever approximation methods. The Greeks, for example, would measure the sun's noon declination for several days before and after the expected solstice date.
Okay.
Then they'd look for 2 different days, one before and one after, that had the exact same noon declination. The thinking was that the true solstice must have happened exactly halfway in time between the noon measurements on those 2 days.
Ah, finding the midpoint between 2 identical measurements. Clever.
It was quite ingenious for the time. Nowadays, of course, with modern astronomy and computation.
We can nail it down to the second.
Pretty much. Astronomical almanacs define the solstices based on the sun's apparent position along its path, the ecliptic. It's when the sun's geocentric celestial longitude hits exactly 90 degrees for the June solstice, or 270 degrees for the December one.
Geocentric celestial longitude, a precise coordinate.
A very precise coordinate. And the reason the dates wobble slightly, June 20th, 21st, or 22nd, and December 20th through 23rd, is mostly because Earth's orbit takes about 365.25 days.
The leap year factor.
Exactly. Leap days help keep the calendar aligned with these astronomical moments over time.
It's amazing that journey from watching shadows to calculating precise celestial longitudes and shifting from the mechanics to the human side. It's just as incredible how cultures everywhere have latched onto these moments. It wasn't just about astronomy, it was deeply cultural, spiritual even.
Oh, profoundly so.
Yeah.
Take the ancient Greeks again. They used the term heliostasio,
Which literally means
stand of the sun, direct translation. They imagined the cosmos as this giant celestial sphere, and the sun moved along a specific path on it called the ekliptikos kuklos, the ecliptic circle. That name, by the way, is related to eclipses, which also happen along that path.
so they saw it as a key part of the sun's journey. And in English, we have a few ways to name them, which can get confusing.
Right. Summer and winter solstice are the most common, maybe.
Yeah, but they depend on which hemisphere you're in, don't they? My summer is your winter.
Precisely. Ambiguous globally. So using June solstice and December solstice is a bit clearer, tied to the month.
I kind of prefer northern solstice and southern solstice. Seems the most unambiguous, telling you which hemisphere the sun is favoring.
That's a good, clear way to put it, yeah. Indicates where the sun is directly overhead.
And then there are the astrological names. First point of Cancer for June, first point of Capricorn for December, which you mentioned something about this earlier. That's not quite accurate anymore, is it?
Ah, yes. The precession effect we'll talk more about later. Because of Earth's long, slow wobble, the background constellations have shifted over the millennia.
So when the June solstice happens now, the sun isn't actually in the constellation Cancer anymore?
Nope. Currently at the June solstice, the sun is actually in the constellation Taurus, and it's moving towards Aries over the next couple of thousand years.
Wow. So the astrological sign is sort of historically fixed, but the astronomical reality has moved on.
Exactly. It's a snapshot from a couple of thousand years ago. But that just highlights how deeply these moments are embedded culturally. Think about the celebrations.
Right. All over the world.
In East Asia, for instance, the solstice is Heizai, summer's extreme, and Dungsi, winter's extreme, are actually seen as the middle of summer and winter in their traditional calendars, not the start.
Middle, not start.
Interesting.
Difference.
And the winter solstice especially, being the darkest day, it's inspired so many traditions about the return of light. You have ancient Roman Saturnalia,
Feasting and merrymaking.
the Persian Yalda, celebrating light over darkness, and of course, many modern holidays cluster around then Christmas, Hanukkah, Kwanzaa, the pagan Yule, all tapping into that theme of returning light.
And the summer solstice, the peak of light.
Also widely celebrated. You have Christian traditions like St. John's Day around June 24th, closely linked, and pagan festivals like Midsummer or Letha, celebrating fertility and the sun's power.
It seems almost universal.
It really does. Indigenous cultures have incredibly deep connections, too. The Mapuche people in Chile and Argentina celebrate Huitrapantu, their new year, around the June solstice.
A new year tied to the sun's return.
Exactly. Yeah. The Aymara in the Andes also mark their new year on June 21st, often with a big sunrise ceremony at Tiwanaku in Bolivia. There's even a noise festival among the Atacama people.
Wow. What about elsewhere? India.
In the Hindu calendar, you have Makara Sankranti around Jan 14th and Karka Sankranti around July 14th. These mark when the sun, sidereally meaning relative to the fixed stars, moves into the signs of Capricorn and Cancer, which is slightly different from the tropical solstices we've been discussing, due to that precession wobble again.
Okay, another layer of complexity. And people still mark these today in new ways, too.
Absolutely. You've got things like the huge, colorful Fremont Solstice Parade in Seattle,
Yeah.
or people gathering at ancient sites, like the reconstructed Cahokia Woodhenge in Illinois, specifically to watch the solstice sunrise align.
Even at the South Pole.
Right. The Amundsen Scott South Pole Station has a midwinter party on June 21st. They've been in darkness for months, so celebrating the halfway point, the turning towards the sun's return, is huge. It shows that fundamental human need to mark these celestial turning points.
It really does. Which brings us back to that long-term wobble you mentioned, the precession. This idea that the solstices aren't just fixed points in the calendar, but they actually drift against the background stars.
Exactly. It's called the precession of the equinoxes. Imagine Earth is like a slightly wobbly spinning top. That slow wobble over about 26,000 years causes the direction the North Pole points in space to trace out a huge circle.
Okay, a very slow wobble.
Very slow. And this means that our view of the constellations from Earth at specific points in our orbit, like the solstices or equinoxes, gradually changes.
So the constellation the sun appears to be in during the June solstice slowly shifts over centuries.
Precisely. You gave the example earlier. The June solstice point used to be in Cancer thousands of years ago. It moved into Gemini around the year Nashen 10th.
Okay, around the start of the Common Era.
Then it slipped into Taurus relatively recently in 1989, and calculations show it's heading towards Aries, expected to cross into that constellation around the year 4609.
Wow. And the December solstice does the same.
Same process, different constellations. It moved from Capricornus into Sagittarius thousands of years ago. It's projected to enter Ophiuchus.
Ophiuchus, the unofficial 13th zodiac constellation.
That's the one, expected around 2269, and then eventually into Scorpius way down the line, maybe around 3597.
It really puts things in perspective, doesn't it, thinking on those timescales?
It absolutely does. It shows that even the seemingly fixed backdrop of stars is part of this grand, slow, cosmic dance relative to our earthly seasons. Nothing is truly static.
So we've really covered a lot of ground today, from the basic mechanics of Earth's tilt causing seasons and solstices,
The core science.
to the etymology, the sun standing still, the challenges of measuring it, and this incredible tapestry of human culture celebrations, calendars, ancient observations.
All woven around these two specific moments in Earth's orbit.
It really shows how these aren't just, astronomical footnotes. They're deeply tied to our planet's life cycle and human history.
Absolutely. Which kind of leads to a final thought, doesn't it?
Go for it.
Well, knowing how deeply intertwined human cultures have been with these celestial rhythms for literally thousands of years, it makes you wonder, how might you, listening now, find new ways to connect with the turning of the year? Especially now, maybe armed with a bit more understanding of what's actually happening up there.
That's a great question. Maybe it's about more than just noticing the longest or shortest day.
Perhaps, yeah, a different kind of awareness.
So the next time a solstice comes around, maybe you take a moment, look up, or just feel that shift in the light. Ponder that idea of the sun standing still, and think about that amazing life-giving tilt of our planet.
A moment of cosmic connection.
Exactly, a moment of profound alignment happening right here, right now, for all of us on this tilted little world.